Color detection using KNN, the K nearest neighbor algorithm. Welcome to our presentation. My name is Hitinder Sidhu, and I'm here with team members Omar Al-Sumeri, Jacob Lascombe, Drake Sheila, and Luis Villanueva. In today's discussion, we will begin with the individual contributions followed by a background of the KNN algorithm. We will then cover the proposed improvements on the existing naive solution, along with an overview of the pseudocode. We will then discuss the experimental results with analysis, followed by a demonstration of the implementation of our program, and then finishing with some concluding remarks. All right, let's go ahead and begin with the individual contributions.
My contributions to the project are the C++ naive program, testing and debugging of the algorithms, the time complexity analysis, and the OpenCV implementation.
My contribution is the C++ program, improved program, time complexity analysis of that program, background, space complexity analysis, testing and debugging of algorithms.
All right, and my contributions include the problem statement, methodology design, and result analysis for the report. I was also the primary proofer and editor for all documents, and I provided feedback for improvements in design, execution, and reporting, as well as testing and debugging of our C++ program.
I worked with finding limitations of the existing work as well as abstraction of our design and implementation. I also worked with the analysis of accuracy between the naive and improved algorithm.
I designed a C++ 3D graph program for data visualization to help test and analyze the experimental results, and tested and compared accuracy between both the naive and improved algorithms.
And I'll be talking about the background for this project. KNN stands for K's nearest neighbor. It is a simple and widely used algorithm for both classification and regression tasks in machine learning. In KNN, the algorithm predicts the class or value of a sample based on the majority vote or average of K nearest neighbors in the training dataset. The K in KNN refers to the numbers of neighbors that are considered when making the predictions. As we see here, an example is shown on screen. An example is having two classifications, dogs and cats. The axis represents their weight, and on the y-axis, their weight on the y is represented by the y-axis, their height is represented by the x-axis. If they have a small weight and small height, they are a cat. If they have a large weight and large height, they are a dog. Random points in green represent cats, while random points in red represent dogs. If a new point is input in orange, while k is set to 3, all the points on the graph have their distances compared using a Euclidean distance to the orange point, and the 3 closest points are tallied up from classification. In this case, all 3 closest points are green, classifying the point as a fat cat. The square root of k is normally used in KNN. The square root of k reduces the number of neighbors considered compared to using the actual value of k. It strikes a balance between considering a sufficient number of neighbors to make accurate predictions and avoiding overfitting or being overly influenced by noisy and irrelevant neighbors. The square root of k can be a reasonable choice, especially when dealing with larger data sets. It can help in reducing the computational complexity of the algorithm while still capturing the essential characteristics of the data. KNN has its strengths in simplicity and interpretability, but it can be computationally expensive for larger data sets and high dimensional feature spaces. KNN remains a popular algorithm for various tasks due to its intuitive nature and competitive performance on many data sets. I'll pass it on to Hit to talk about the proposed improvements.
All right, thank you, Drake. And now I'll be going over the proposed improvements on the KNN algorithm. As we saw, KNN is a powerful classification algorithm. For the purposes of our application, we will be using KNN to classify colors based on their RGB values. In the naive implementation, multiple pre-classified data points are used, requiring the calculation and sorting of numerous distances, which in turn adds to the time and space complexities. As we saw, the naive algorithm uses the square root of n for the calculation or for the value of k, with n being the number of pre-classified data points. And we improve upon the performance of the naive algorithm by having one representative for each cluster of data or each color, and making k equal to 1, only considering the closest neighbor to the unknown data point. This improvement on KNN works best when the data points are condensed clusters. In addition to our color classification algorithm, this improvement can be applied to other applications where the data points are condensed clusters. This improvement will reduce the number of distance calculations and remove the dependency on sorting algorithms. In theory, space and time complexities will be significantly reduced while maintaining accuracy of the algorithm due to the dataset structure. And now I'm going to go ahead and pass it over to Omar.
Thank you, Hit. The next section of our presentation will speak about the pseudocode for the naive and improved implementation. I will first speak about the pseudocode for the naive implementation. We had to create our own pseudocode and C++ program for the naive implementation since we had a particular application for the improvement on KNN. Our first step is to create a data type color, which will have 3 integers, red, green, and blue. 1 double, which will be the distance calculated from the color point to the unknown color, and a string, which will be the color classification of the specific color. Our first step is to create a list that will contain all the colors in our color set. The colors that we'll be classifying are red, blue, yellow, green, orange, purple, black, and white. With the assistance of an online RGB color coach chart, we assured that each color is an accurate representation of the color it will be classifying. The next step will be to find the distance from the unknown color point to all the other points in the list, using the distance formula shown in the right figure. Taking that list of distances, we will now sort them using 2 different sorting algorithms, one with a time complexity big O of n log n, and the other having a time complexity of big O of n squared. Our reasoning on using 2 different sorting algorithms with 2 different time complexities is to show that no matter the time complexity of the sorting algorithm, the time complexity of KNN will still take a hit since we're using a comparison-based sort. Our next step is to now classify the unknown color using KNN. The naive implementation of KNN, k equals square root of n, will be used here. Taking the list of sorted distances, we start from 0, increment to k, taking note of the colors that occur the most in that increment up to k. Whichever color occurs the most will be classified to the unknown color. Drake will now speak about the pseudocode for the improved implementation.
Thank you, Omar. As Omar said, I'll be going over the pseudocode for the improved implementation. The best a naive KNN solution can run time complexity-wise is n log n. With the improved algorithm, the time complexity is a constant c, c being the number of classifications or colors to detect. This is due to the reduced steps and reduced data points needed to run the algorithm. There are 3 main steps for running this improved algorithm. Calculate distances to all C color classifications to the new point, find the smallest distance in the color classifications list, return the smallest distance which classifies the color. This algorithm will get the distances to a limited predefined amount of colors instead of all the points stored in a classified points list. Finding the smallest distance is determined by comparing each element in a limited list of predefined colors to a temporary variable. The smallest distance is stored in the temporary variable, first storing the first element at the start of the searching process. If a smaller distance is found, it replaces the current smallest distance. The closest distance to a predefined color determines the classification. This allows the improved algorithm to run at theta c due to cycling through the predefined constant list once. This algorithm does not need to tally up the closest k neighbors because the closest point should equate to the correct classification, making k in this scenario 1. Due to not storing a collection of predefined points, there is also an improvement in space complexity. The naive algorithm takes n times c, where n is the number of pre-classified points each group of colors will be populated with, and c comes from there being a constant amount of specified colors. The improved algorithm only takes theta c due to having c predefined color points. By setting each color to have 1 main point and classifying new points based on which the main color point is closest to, the time complexity was improved from n log n to c, and the space complexity was improved from n times c to c. I'll pass it on to Jacob for the analysis of the algorithms.
Now we'll be talking about the analysis and results from our experiments. For our project, we conducted a series of 3 experiments to evaluate and compare our improved implementation against the naive implementation. These experiments were designed with specific objectives in mind: testing time complexity, assessing accuracy, and evaluating space usage. The time complexity experiment, its purpose was to test the improvement on execution time. Our accuracy experiment validates the effectiveness of the algorithms, and our space complexity experiment tests the space utilization of each algorithm. Now I'll be handing things off to Louise, who will be talking about time complexity.
Thank you, Jacob. Here are the experimental results for time complexity. As you can see, we have two graphs. On the left side, we have a graph with the improved algorithm, as well as two implementations of the two different sorts. So the two different sorts were the ones that took as n squared and n log n. So on the graph, the x-axis is the number of inputs taken into these algorithms, and the y-axis is the amount of time it took to run these algorithms. So as you can see, the gray line is the n squared, and that is the worst performing one that we have. The next graph on the right has a representation of the improved algorithm with the fastest n log n, being the blue line. As you can see, the orange line stays relatively constant, while the n log n line is increasing with more inputs being input. So now let's analyze these results. So for the time complexity, we used a bubble sort, and then we used a best comparison sort because we need to compare and sort all of the inputs, all of the input to all of the data set points that we have in our system. So n is the total number of data points in the system, and that will need to be compared and sorted, so that way the k number can be chosen from these sorted points. On the other hand, in our improved algorithm, we only have a theta of c, and c is the number of predefined color classifications that need to be done. So for every new data point, there will only need to be done a classification comparison between this 8, and the shortest distance found will be the classification given to that new data point, meaning that we have a constant value of c for each new data point being input. I'll pass it on to Jacob to talk about the accuracy.
You can see the experimental results for the accuracy tests for both the naive solution and the improved solution in these tables. The RGB inputs are shown in the cells of each table, while the background colors show what our algorithms classified each color as. The labels at the top of the column show what the expected color value should be. Our accuracy experiment aimed to investigate the trade-off between accuracy and time complexity, expecting a potential compromise in accuracy for improved performance. However, the outcomes we obtained challenged our initial expectations. To conduct the accuracy experiment, we employed a data set consisting of 8 sets of 6 data points, each representing a different color to be aimed to detect. This amounted to a total of 48 data points that were thoroughly tested for accuracy. Contrary to our assumptions, the results obtained from both the naive and improved solutions turned out to be strikingly similar. However, the improved solution unexpectedly outperformed our predictions, delivering superior accuracy while also maintaining enhanced efficiency. The naive solution achieved an accuracy rate of 68.8%, providing a benchmark for comparison. Surprisingly, our improved solution surpassed expectations by yielding an accuracy rate of 70.1%. This demonstrates that our improved algorithm not only delivered the desired performance, but also exhibited notable accuracy, defying our initial concerns. And now I'll hand things off to Luis, who will be talking about the space complexity experiment.
Here we have the experimental results for the space complexity. So we conducted 3 different experiments, 2 for the naive and 1 for the improved. The first naive experiment used 1,000 new data points with 100 pre-classified points per color. So we had 8 colors that were defined, and we had 100 points for each one of them, meaning we had 800 points in the system, in the memory, that needed to be sorted and compared for each new data point. So for each new 1,000 data point, there was 800 points for each one of those 1,000. Then for the second result, so we can see a bigger disparity between the memory usage. We did 1 million pre-classified data points per color. So that means we had 8 million pre-classified points in total for each new data point, meaning that we had 1 million for each new data point. The space complexity be seen in the figure 1 and figure 2. Figure 2 has the 813 megabytes, while figure 1 has 1.8 megabytes. That means that there's a big difference between how much data points resulted and how much memory was used. In the bottom figure, we have our improved algorithm. So for our improved algorithm, we only ever had 8 predefined colors. We didn't increase these probably stayed constant. So for each new data point, we only used 8 predefined colors, and the memory stayed at around 1.6 megabytes. Let's analyze these results. So for the naive implementation, as you can see, we require a pre-classified data to classify new data, meaning that we need to have already an amount of data in the system to be able to define new points. So our spacing complexity is big O of n times c, c being the number of pre-classified data per n color. So earlier we had c being 100 and the 8 being the n. So that means we had an O of 800 for the first test. So the larger the data, the better it is in terms of having a better accuracy, but this will affect how much space we will use. In comparison to our improved method, we only ever require main colors to classify new data, meaning we will only ever store up to the C predefined colors. And in the previous slide, we discussed we only ever used 8 colors, meaning that we had a space complexity of theta of 8 being C. So that means we had a constant value of space memory for every point. Now let me pass it on to Omar to show the of our implementation.
Thank you, Luis. I'll now speak about the OpenCV implementation in our project. A little background about OpenCV. OpenCV is an open source library that focuses on image processing and video capture. Our motivation for the OpenCV implementation was to have our algorithm interact with the real world, and hopefully have it implemented in the real world scenarios, such as seeing if fruit is ripe or not. For this project, once the run button is hit on the program, the default camera will open up and a video live stream window will be displayed for the user. A white box will be in the live stream window for the user to place an object in the white box to classify its color. The average RGB values from the pixels within that box will then be inputted into the improved algorithm to classify the color of the object. To the left, there will be a terminal outputting the color that it detects in the white box. We will now have a live demonstration of our OpenCV project. We'll be classifying 3 different objects: a yellow towel, which I'll begin with. As we see on the left of the terminal, the color is yellow. A red medicine cap. So you see the colors that is being detected is red. And lastly, a green folder. And as we also see on the terminal, color is green. That is a live demonstration of our OpenCV implementation in our project. I'll now pass it off to Hit for the concluding remarks.
Wow, all right. Thank you for that, Omar. And in conclusion, we'll go ahead and review that we saw that the KNN algorithm is a powerful algorithm for classification problems. We applied a naive solution to the classification of colors, and then with the observation that RGB color point data consisted of condensed clusters, we implemented an improved solution to the KNN algorithm. The program best executes when the predefined colors of the algorithm are calibrated to the colors that will be detected by the camera. In our improved algorithm, we observed a significant improvement in both time and space complexity, while still maintaining a consistent accuracy, accomplishing our objective of an improved implementation of the KNN algorithm. And that concludes our presentation. Thank you.